Hello, my name is Alexis Ravenscroft. Today I'm going to be discussing my summer project. My summer project is on catalytic chemistry of novel boron-fluorine functionalized drug-like molecules. A little bit of background for this project is it began quite some time ago when the POP group began researching ways to create valuable new carbon-carbon and carbon-X bonds. And they found that transition metal catalyzed bore carboxylations can deliver densely functionalized carboxylic acid products. And they revealed that bore carboxylations of alkenes can be achieved under mild conditions and yield novel organoboron compounds. Organoboron compounds can be utilized in synthetic organic and organometallic transformations. They can allow for rapid chemical diversification, and they can increase chemical complexity. And boron-based drug candidates are also gaining popularity in the pharmaceutical community. My project starts with the creation of the difluoroborolactinate, which begins with a bore carboxylate, which contains the carboxylic acid and a B-pen group. It gets reacted with KHF2, which then creates the difluoroborolactinate. And I've done this with multiple substrates, replacing the R group with tert-butyl, metamethyl, just a styrene derivative, isobutyl, methoxy, and paramethyl. Once generating these products, I have to make sure that they're there using NMR spectroscopy. And I know that this product is here because of its hydrogen spectroscopy. The hydrogens H and H prime, because of stereochemistry, end up being in two different positions despite being on the same carbon. And fluorines end up being separated as well despite being on the same boron due to the stereochemistry. The boron ends up being a very broad peak because of the difference in spin between boron and fluorine. After assuring that the generation of the difluoroborolactinate occurred, we take these and we start the next part of the project using the Nobel Prize winning Suzuki-Moira cross-coupling reaction shown in the top right. And so instead of using the B-pen group, we're going to see if the difluorine affects it. And so my proposed Suzuki-Moira cross-coupling mechanism shows instead of using the B-pen, it uses the two fluorines. And so what we're hoping to see is a change in need for catalyst, maybe a reduction in catalyst, or an increase of speed in this second transmetallation step to progress the reaction further and be more beneficial than the parent B-pen. So far, I've only done preliminary testing, but I have done the cross-coupling reaction to a rather low yield, but have proven that the lactinate can indeed produce the 2,3-diarylpropionic acid by looking at the HNMR and the ABX pattern, which I've highlighted with different colors on the hydrogens above and on the NMR spectrum. And so in my conclusions, it's the fluorination procedure can work for many types of bore carboxylates, and I will later on expand upon that even more with a wider range of substrates. And cross-coupling reactions will produce the hypothesized 2,3-diarylpropionic acid, but I need much more studying and practice to increase my yields and make varied tests to examine its catalytic benefits. And so I'd like to acknowledge my whole entire group, the POP group, as well as specifically acknowledge my mentors, Randika, Mason, and Dr. Pop. And I'd like to thank the SHORE program for giving me this awesome opportunity to work over the summer and help me and guide me through my research. And yeah, thank you so much. Have a great day.